Alright people, welcome back. Let's jump into section 2 on our series on pharmacokinetics. And we are going to talk about absorption and bioavailability today. So quick review from the last lecture. What did we do then? Well, first we defined pharmacokinetics, and you need to know this before we move on. And so pharmacokinetics is really looking at the change in drug concentration as the drug moves through the different compartments of the body. So as the drug moves through your body, how does its concentration change? And we are going to talk about absorption today. And absorption is really the process of a substance entering the systemic circulation. And so we are going to look at how the concentration changes as a drug enters the systemic circulation. And just a little key point to remember is that absorption is highly dependent on the route of administration. So let's get to our most important concept of the day first, and then we'll get to the good stuff. So the most important concept. Well, this is something that you probably learned in high school. And what is that? Concentration is equal to mass over volume. Super simple. You must know this. But in terms of pharmacology, what are we talking about? Well, when we talk about the mass, we're really talking about how much drug we gave, right? If you look at the dosages for most drugs, it's given in milligrams. So that's referring to mass, the amount of drugs given in milligrams. Volume is a little variable. So if we're talking about blood volume, we might use, liters. If we're talking about the volume in a syringe, we might use cc's or cubic centimeters or milliliters. I want 5 cc's of epinephrine stat. In any case, the volume depends on what you're dissolving it in. So the drug is dissolved in a certain volume, and that gives us our concentration. So what are some common volumes? Well, blood volume. Blood volume is about, give or take, 5 liters. And commonly used as opposed to blood volume, which is not really used when we talk about pharmacokinetics, is plasma volume. And so plasma, as you know, relates to blood in that it's, you take the plasma, you take the blood, throw in a centrifuge, you get out that pale yellow substance, and that is your plasma. And so it's your blood volume, let's just say your blood volume minus the cells. And your cells make up about 50% of your blood. So that leaves us with 50% left, and that's about 2.5 liters. Now, on an exam, you might see this actually written a different way. So they might write out that your plasma volume is equal to your blood volume times 1 minus your hematocrit. So remember, hematocrit is what? It's the volume, it's a percentage, and it's the percentage of your blood volume that the red blood cells take up. And so if I was going to multiply this out, right, I would get blood volume times 1 minus my blood volume times my hematocrit. Right? And that makes sense. This right here is the cells. So just in case you saw this a different way. And finally, just to remind you, 1 cc is 1 cubic centimeter, and that is equal to 1 milliliter. So let's do a problem and solidify this concept. Concentration is equal to mass over volume. So a 10 milligram dose of drug X is 100% absorbed. What is the plasma drug concentration? So first off, 10 milligrams, that is what? That is our mass. That's the amount of drug. And we know it's 100% absorbed. So the only way anything is ever 100% absorbed is if you give it IV. And when I say absorb 100%, that means that it's all getting into the plasma. It's all getting into the plasma. So what we want to do is figure out the plasma drug concentration. So the concentration in the plasma is equal to the mass over the volume. So what is the mass? Well, the mass is the 10 milligrams of drug that I gave. And what is the volume? Well, we just said the volume of the plasma is 2.5 liters. So overall, I get a concentration in the plasma of 4 milligrams per liter. And we're going to come back to this number on the next slide. So here's our case, and it's our in case. So we're talking about drugs getting into our body. So we're going to give a drug IV bolus. This means intravenously, and bolus means that it's all at once. And it goes into one compartment, and that compartment is the plasma. So this means no distribution. No distribution. And we also assume here that there is no elimination. So this is, honestly, this is the easiest case that we can do. So we start off by administering this drug IV bolus, and we want to get it into our systemic circulation. So let's just draw a little picture here. Here is our syringe. We give this drug IV bolus, and there's a certain volume of drug in here, and there's a certain concentration of that drug in here. And so remember, concentration is equal to what? Concentration is equal to mass divided by volume. We'll get back to this in 1 second. So what we want to do is draw a little graph. And on the y-axis of this graph, we're going to put the plasma drug concentration. And on the x-axis, we're going to put time. And so if I was going to draw a graph here, well, I would say I gave a fixed amount of drug, right, a certain amount, and it goes into our systemic circulation. So this is, let's say, our blood volume or our plasma volume. And it has nowhere to go. There's no exit. So I'm going to get a set concentration, and because the mass is set, how much drug, the volume is set, and it doesn't go anywhere, so I just get a graph that is pretty boring. It's a straight line all the way across. And there is no elimination, so this is a straight line. Now, I really can't do it like this. I need to actually see some numbers. So numbers help me. I think they actually help everybody. So let's start off by figuring out, let's figure out the plasma drug concentration. So in order to figure that out, I need to know what was the total mass of drug I gave and the total plasma volume. So first off, let's say I gave 10 cc's. So 10 cc's means that the volume total was equal to 10 milliliters. Now, that doesn't mean anything to me because in order to figure out how much drug I gave, I need to figure out the mass. So volume times concentration is equal to mass. So let's give you a concentration. Let's say the concentration of drug in this syringe is, let's say it's 1 milligram per milliliter. Well, using this, I can now figure out the amount of drug I gave. So the volume in the needle is 10 milliliters. The concentration in the needle is 1 milligram per milliliter. And so just by looking at this, if I multiply these two numbers together, milliliters will cancel out, and I get the amount of drug given, aka the mass. And so I do that, and I see I gave 10 milligrams of this drug. So the mass is equal to 10 milligrams. Now remember from that last slide, we had blood, which is about 5 liters, and plasma, which was the blood minus the cells, is equal to 2.5 liters. So if I want to figure out the plasma concentration, and the brackets indicate concentration. Remember, concentration is equal to what? Mass over volume. Mass is the amount of drug I gave, which is 10 milligrams, and the volume is equal to 2.5 liters. So from the last question, we remember that is 4 milligrams per liter, and that would be what we have here. And again, remember, I gave this injection at time t equals 0, and we assume that it all gets absorbed into our plasma. Now what we're going to do is look at something, and we're going to come back to it in a little bit. But what we're going to look at is the area underneath this curve. So to do that, let's give you some values here. Let's just say this is a total of 4 hours time. If I was going to calculate the area underneath this curve, I would say, okay, the AUCIV. And why is the area underneath the curve important? It gives us a sense of how much of this drug we absorbed. So I would have 4 milligrams per liter here, because this is just a rectangle. And about 4 hours went by, and I would get something about 16. So let's keep that in the back of our head. One last thing. In your book or in other books, they might not write this as plasma. They might actually write this as serum. Really, there's very little difference between plasma and serum. Serum is just plasma minus the clotting factors, and a common clotting factor, referred to as fibrinogen. But just remember, serum is plasma minus the clotting factors. All right, so this is IV bolus. We gave 10 milligrams total. Let's take this exact same 10 milligrams, and instead of giving it IV, let's give it PO, or by mouth. So here is our second case, and it's the second easiest case we can deal with. We're giving the same amount of drug, PO, and so PO means per os. Os means mouth or opening, like the cervical os. And so another way you can think of this is per oral, or by mouth. It's still going into one compartment, no distribution, and again we assume no elimination. So we start off by administering this drug. We give 10 milligrams by mouth, and we want to get this drug into our systemic circulation. But unlike before where we could inject it directly into the systemic circulation, we have to swallow the pill. So what are the process? What's the process as we swallow this pill? Well, first it needs to go into our stomach, and it churns with all that stomach acid, and eventually it works its way through our duodenum into our intestines. And in this process, though, we might lose a little bit of the drug. Think we have all the stomach acid, yada, yada, yada. Now it's in our intestines, and it needs to cross our enterocytes, go through our, intestinal circulation, our superior mesenteric vein, inferior mesenteric vein, portal vein, to get into our liver. And again, we might lose a little bit more drug here. So let's just write, you lose some drug. How much drug do we lose? Let's say from here, from the stomach to the intestines, and I'm just making up numbers here, we lost 2.5 milligrams. And as we're going from our intestines to the liver, we lost another 2 milligrams. And from our liver, it needs to get into our hepatic vein, into the IVC. Once it gets in the IVC, it's in our systemic circulation. And even here, let's say we lost another 0.5 milligrams. Well, if I add these up, 2.5, 2, and another 2.5, in total, I just lost 5 milligrams of drug. So that's important to remember. So now let's draw a graph. And we're going to put plasma drug concentration on the y-axis like we did in the past, and we're going to put the time on the x-axis. So if I lost 5 milligrams and I started with 10, how much do I have left? 5. So now my plasma drug concentration is just the 5 milligrams remaining, and the plasma volume is 2.5 liters, 2.5 liters, and so this concentration is equal to 2 milligrams per liter. So we can see right off the bat that the maximum concentration that we can get is 2 milligrams per liter, whereas before we had 4 milligrams per liter. So if this was 4, let's say this here is 2. So that's one component, and that is that we have actual less drug, or a lower plasma concentration, because we have less total drug. The other factor we need to consider is that this actually takes time. So if this was t equals 0, by the time we get to t equals 1 here, this is a curve. It doesn't all occur instantaneously. So if I was going to draw this graph, I might get something that looks something like that. And so the process of going from before our plasma circulation to our plasma circulation, right, this is our absorption. A-B-S-O-R-P-T-I-O-N. Remember, absorption is the process of the drug getting into our systemic circulation. Now, let's look at the area underneath this curve. And let's just assume this is a rectangle again. So if this is 4 hours, Well, I have 2 on this side, 4 on that side, and remember, I don't absorb it. I have this kind of curve going up, so I'm probably a little bit less than 8 hours, or 8, right? So if I was going to write the area underneath the curve, PO, it's probably around 8, maybe a little bit less than that. And so I can write here, let's write it right here, that the area underneath the curve, PO, we now know is less than the area underneath the curve, IV. Now, this just means that I've absorbed less total drug by mouth than I have IV. And that's what the area under the curve tells us. But we don't use this representation. And there's a term that we use that defines the fraction of drug that gets absorbed into our systemic circulation. And that term, my friends, is bioavailability. Bioavailability. I can't spell. Bioavailability. Bioavailability. And so what bioavailability is the, in this scenario, is the area underneath the curve PO divided by the area underneath the curve IV. And so we're going to talk about this more in detail on the next slide, but remember that this gives us the fraction of the amount of drug that gets into our systemic circulation. And it's a fraction in relation to how much would have gotten in if we gave it IV. So remember this term, it's huge. So before we jump into bioavailability, here are your 4 stop, think, and repeat questions. If you want, press pause and answer these questions before moving on.